y0. What I do is I look at this particular equation and I replace x by x0 and y by y0 and solve for c. And by the way, I would intuitively expect to be able to find that value of c, because after all I have an arbitrary constant in here, which means I have a degree of freedom, and therefore I would suspect that by replacing x by x0 and y by y0 I should be able to find a specific value of c. Now, notice what this leads to. If I replace x by x0, y by y0, I get y0 equals x0 squared plus c. Consequently, c is y0 minus x0 squared. x0 and y0 were specific numbers, real numbers. Consequently, y0 minus x0 squared is a specific number. And consequently, the specific choice of c, such that the equation becomes what? Y equals x squared plus the constant y0 minus x0 squared, is the only solution of what the equation dy dx equals 2x that passes through the point x0, y0. This is kind of baby stuff in terms of the fact that it was elementary in part 1 of our course. But remember, this solution set is what? It's a set of parabolas which are essentially a parallel family of parabolas, and what you're sort of saying is, gee, it seems obvious geometrically that since I have this infinite family of parallel parabolas, that specifying a point that has to be on the parabola uniquely determines a member of that family. At any rate, I don't want to belabor this point. I want to get to the greater subtleties that come up in handling first-order differential equations. So I've picked a slightly tougher problem, for example 2.